In section 7, we're going to get away from lines just a little bit and graph absolute value equations. So these will still kind of look like lines, but it won't just be one straight line. Something's going to happen when we graph absolute value equations. So we're going to look at the definition of that, or look at like the most basic graph we could do. And then I'm going to have you play with Desmos a little bit to see what happens as we change some things in the equation. And then we'll do a couple examples together. So the most basic, the simplest absolute value equation that we could graph is y equals the absolute value of x. This is something that we'll refer to as a parent function. Okay? Because, again, this is the most simple, the most basic, or the starting point for graphing absolute value equations. Just like when it comes to lines, y equals x would be the parent function of lines, and then everything is kind of some variation to that, right? We multiply that by some constant, and that's the slope, or we can add or subtract something at the end. And we end up with a line still, just like y equals x, but it looks a little bit different. Kind of like parents to their children, right? They look a little bit different, but they're still kind of the same thing anyway. So here, this is our most basic one. We could multiply or add or subtract things in there, and that will change things, but it's still going to look like the parent function, y equals absolute value of x. So we'll just do a real quick plot of this. It should be pretty simple. If we plug in 0 for x, the absolute value of 0 is 0, right? For I plug in 1, the absolute value of 1 is 1, so we have the point 1, 1. Absolute value of 2 is 2, so we'd have the point 2, 2. Absolute value of 3 is 3, so we would have the point 3, 3. Now going to the negative side, if I plug in negative 1, right, the absolute value of negative 1 is a positive 1. Absolute value of negative 2 is positive 2. Absolute value of negative 3 is positive 3. So basically, I just made a XY table, right? And then it went 3, 2, 1, 0, 1, 2, 3 for absolute value. And this is the graph that we get. So instead of one continuous line, we end up with this V-shaped graph. Okay? We still have a y-intercept or an x-intercept, but then we also have this special point down here where we have that turn. That is called the vertex. So the vertex of this absolute value graph is at 0, 0. The vertex is the highest or lowest point of the graph. If you remember graphing parabolas, a parabola had a vertex as well. So that'll be a term that we'll use. So getting to this next slide, this is going to be the general form for all of the, I guess we could call them children, absolute value functions. Okay, so we could maybe take a number and multiply that by the front. So we could graph something like y equals 2 times the absolute value of x, and I wonder what that would do to our graph. Or we could add or subtract something inside of the absolute value. So we could do something like y equals x minus 4 and see what that graph looks like. Or we could add something at the end and graph y equals the absolute value of x plus 1. Or we could do all of those at once. Y equals 2 times the absolute value of x minus 4 plus 1. And what's going to happen to that graph compared to y equals absolute value of x. So what I'm going to have you do is use Desmos, and you can either do this on your computer or there is an app for it. And I've got a screenshot here. So you're going to go to Desmos, and on the first line to enter an equation, enter y equals a absolute value of x minus h plus k. And once you do that, it should pop up like right below it here with an option to add sliders for a, h, or k. And I think there's a button to also click all. So you could add sliders for all of those. And what that's going to do is add some sliders here. So what you'll do with those is you can take and drag these around, or even click this little play button, and it'll bounce them back and forth automatically. But play around with each of these sliders to come to a conclusion, as to what A does to our absolute value graph. What does that do to the shape of it? Does it move it someplace? What happens? Same thing with H. Move that around, see what effect this has on your graph, and then same with K. Move that around, see what effect that has on the graph. Okay, so pause the video, go do that. When you think you've got those figured out, the video will come back to the video and it'll resume, and I'll sum up the things that you should have discovered. So you've played with Desmos and you should have discovered the following things. You should have discovered that the A in front is kind of like our slope. That can either like steepen or flatten or narrow or widen our graph. It opens or closes that V, right? If it's a 2 or a 3 or a 4, we got narrower. If it was something like a half or a third, then it opens out wider, right? The other thing that happens is if A goes negative, then that V flips over, and that V is now opening down, right? What you should have discovered about H is that it shifts the vertex left and right. And the tricky part here is that it's opposite of what we see. So if we see an absolute value equation that has y equals the absolute value of x minus 2, intuitively we probably want to go left 2, so 2 in the negative direction since it's x minus 2. But this shifts us right 2. It would move our vertex to the right 2. And if we saw x plus 2, that would end up moving us to the left. So it's the opposite of what we see there. And then what you should have discovered about k was that shifts the graph up and down. And that one goes exactly as we see it. So if we see the absolute value of x plus 3, then that does in fact shift our vertex up 3 units. Okay. This is a pattern of behavior that we're going to use in the future for other functions as well. We could graph parabolas this way. Instead of absolute value, it could be squared, and that gives us parabolas. We'll also look at this with square roots and see how those different things affect the graphs of those. So this is a pattern that we'll see again and again as we look at different types of functions throughout Algebra 2. So let's do a couple examples together, and I'll show you what I'll expect to see when you graph these. So when you graph these, I'll expect that you kind of compare this graph to the graph of y equals absolute value of x. So first of all, on this one, we have just absolute value of x. So it does not move left or right. Right? It's x plus 0. It doesn't move anywhere. But then we have this plus 3, which is going to shift us up 3. So I'll expect to see you write down that we're moved up 3. If we don't move right or left, but we move up 3, then our vertex is shifted just up 3. So that's at 0, 3. All right. So our vertex is at 0, 3. And then what does this 2 do to our graph? Well, that's kind of like our slope. So that's a slope of 2 now, so it's going to go up a little bit faster. So this graph is narrowed. Right? That V is closed in a little bit. So we have our vertex plotted, and we know that it opens up, and it's basically got a slope of 2 on either side. So from our vertex, I'm just going to go up 2 and over 1, up 2, over 1, and there's half of our V. And we can do the same on the other side. Up 2, over 1, up 2, over 1, and there's our V on the other side. So how about example 2? So in this case, we have x plus 1, which moves us the opposite direction than we would think. So we move left 1, and this minus 2 at the end moves us down 2. So if we move left 1 and down 2, then our vertex is at -1, -2, -1, -2. And then what does that -1/3 do to our graph? So first of all, it's negative. So our V is going to open down. So it opens down. And then it's got a slope of just 1/3, which is a shallower slope. So it opens wider than our normal absolute value of x. So this graph is widened. Okay. So again, from here, we're going down 1 and over 3, down 1, over 1, 2, 3, down 1, over 1, 2, 3, and now I'm just guessing, but that's okay. But there's half of our V, and then down 1, over 1, 2, 3, down 1, over 1, 2, 3, and there's the other half of our V. Not perfect, but we got the job done. Okay? So make sure that you show me and write out these pieces of information, because that shows me that you understand what these values in the equation do to this graph. You can use a graphing calculator or Desmos to help you out if you want as you're doing the homework. But if all I see is a drawing of the graph, then maybe all you did was plug that equation into your graphing calculator and trace what your graphing calculator spits out, and you don't actually understand what any of this does to our graph. So I want to see these parts written out when you do these graphs, okay? But that should get you through the assignment for this section.